we're talking about how to solve quadratic equations, and today we're introducing something that you've never actually seen before. All right, so whether you remember it or not, most of what we've done so far you've seen before. Today is not something you've seen before. It's totally brand new for Algebra 2 students. So, but to get there, let's refresh ourselves on some of the methods that we have for solving an equation, a quadratic equation, an equation with a squared in it. Okay, so these first two, why don't you give them a shot? Solve by factoring. And I'll give you a hint for the first one. Divide 3. Start with a GCF. So divide 3 out. Okay, factor it, and then set each factor equal to 0. That's how we solve by factoring. Okay, give it a shot, and then we'll compare answers. All right, so if you divided by 3, divided the 3 out, what did you get on the inside? Vinny, did you get it?
No, I did not.
Well, what's 3 divided by 3?
1.
Yeah, so 1x squared. And what's 27 divided by 3? 9. 9. Okay? X squared minus 9. Okay? And then this thing can factor more, right? X squared minus 9. Either you can remember the shortcut, difference of perfect squares, or you can put a 0 in the middle. 0x minus 9, and use an MS chart, right? We talked about that last week. So MS, all right, so it's negative 9 and 0. They add up to negative 9 or multiply to be negative 9 and add up to be 0. What two numbers do this? 3 and negative 3. Okay? And so this thing factors into x minus 3 and x plus 3 equals 0. And then, of course, we set each equal to 0. So x minus 3 equals 0, x plus 3 equals 0. Okay? X equals 3, x equals negative 3. And then we should also set this equal to 0. So that one got set equal to 0. That factor got set equal to 0. And this one should as well. But because there's no variable in there, is 3 equal to 0? No, 3 is not equal to 0. So that one does not give us a solution. But the other two do. There we go. X equals 3 and x equals negative 3. Okay, so that's how we solve by factoring. On the second example, we don't even have to do anything to this one for it to be ready for this little MS chart right away. So factors of 50 that add up to 5. Yeah, so 5 times 10 is 50, and then they're supposed to multiply to be negative 50, so we must have a negative on the 5. If they're going to add up to be 5 still, negative 5 plus 10 is positive 5. Okay? So this thing splits up into x minus 5, x plus 10, okay? And then set each factor equal to 0. So that's equals 0. X minus 5 equals 0. X plus 10 equals 0. So x equals what, Colton? 5 and? Negative 10. Excellent. Okay, hopefully you're good at that. Most of you showed me on the quiz that you're good at that, so great work. All right, so that's solved by factoring. And then we have solved by finding the square root. So go ahead and give this one a shot. Solve by finding the square root. Don't distribute the 5. That's not what we're talking about. Don't write it twice and then FOIL it. That's not what we're doing. We're square rooting it to get rid of the squared. That's what we're doing here. But you have to divide the 5 out first. So do that. I'll pause real quick and then give you a shot to do it on your own. Then I'll show you my answer. Okay, so when you divide the 5 out, you are left with this x plus 3 squared. And then what's 25 divided by 5, Aliana? 5. Excellent. And then we need to do the square root to get rid of the squared, which I saw many of you doing excellent work. Okay, square root cancels out the squared. Do it on both sides. And when you get x plus 3 equals the square root of 5. Am I okay leaving it like that, Rachel? No. What do I need to have in there?
Plus or minus the square root.
Yeah, plus or minus square root 5. If you're taking the square root in an equation, You have to include that. You have to include that. All right? So plus or minus 5. And then subtract the 3. So x equals negative 3 plus or minus root 5. Okay? And that's 2 different answers, guys. That's 2 real solutions. Which means those, like if I graphed this, those are actually x-intercepts. They're terrible decimals, but it's 2 different terrible decimals, 2 different places that are really on the graph that the intercept would really occur at. Okay? So those are real. Let's look at this other example. It's going to play out a little bit differently, so I'll run through it really quickly so you can see. X minus 1 squared. I divide the 7 away. And what's 28 divided by 7? 4. And then I take the square root to get rid of the squared. And what is the square root of 4? 2 plus or minus 2. Okay? So whether you end up with a root because it wasn't a perfect square or a nice even number because it was a perfect square, either way you still need to do the plus or minus. Okay? Let's see how this ends. And then, so we're going to add 1. Add 1. So it's x equals 1 plus or minus 2, which means it's 1 plus 2 and 1 minus 2. It's both answers, and you have 2 solutions there. So 3 and negative 1. Again, 2 real answers, 2 actual places on the x-axis where this graph would cross. 2 actual x-intercepts. 2 roots, 2 zeros, right? Remember all of those names we have for the solutions? X-intercepts, roots, zeros, okay? So that is solving by doing the square root. And we're going to skip these because we're going to do a few of those later. Scrolling all the way down to this blank page right here, solving quadratic equations. And I want to pause here. And I want to explore something. So you, in the past, when you come across the square root of negative 4, you have decided, if you were like taking a middle school quiz or something, and they gave you this, you would write no solution. Because you have been taught that you can't take the square root of a negative number. And that's true. Nothing times itself is going to give you a negative 4, right? Because a positive times a positive is positive. A negative times a negative is also positive. So there's nothing that you multiply it by itself that's going to give you a negative. But mathematicians decided that this is not very convenient. And there are reasons why it might be convenient for us to be able to go further with this expression here, with this problem. And so they came up with a solution. They decided, let's make the square root of negative 1 equal to something called I. I, which stands for imaginary. Okay. So this was the imaginary number. I is the square root of negative 1. Okay. So I stands for the square root of negative 1. And let's see how this helps us. Okay. Back in middle school, you were taught that, I'll leave that up there for a moment, you were taught that the square root of one number times another number means that you can split those up into separate square roots, right? The square root of a and b multiplied together, you can give a and b their own root, right? So we're going to do that here. Let's say that 4, the square root of negative 4, is the square root of negative 1 times 4. And then let's follow that little AB example there. That means that negative 1 can have its own root, and 4 can have its own root. And now, I is equal to the square root of negative 1. And so negative 1, the square root of negative 1 really is just I times the square root of 4. And what is the square root of 4? 2. And so this is a convenient way to deal with the negative in a way that you're not just removing it completely, Okay, we haven't forgotten about it. And this new expression that we're left with, 2i, this does reflect that at one point there was the square root of a negative in the backstory of this 2i. Okay, so we're honoring the fact that there was a negative there. We're not just, in math, you can't just erase things because you don't like them. Okay, but this is a more convenient expression for us to use, and you can do a whole lot more with something like this than you can with this. Question?
If the answer to
All right, so this is 2i, and that's great. That's great. So let's apply that down here. And just so you know, I don't expect you to show everything I just showed, every step. I showed all those because I want you to see exactly where this I came from and what happened to the negative. Here's what I would expect you to show. Scroll down. Square root of, here, we'll take this in the context of a problem. X squared plus 4. So subtract 4. X squared equals negative 4. And then square root to get rid of the squared. So x equals the square root of negative 4. And here's how I want you to show this work. I want you to show that the negative in the square root, right there, comes on the outside of the root. It comes out as an I root 4. Okay? And then you can finish this off by saying, this is plus minus, I should say plus minus. X equals plus or minus, the square root of 4 is 2, right? 2i. Okay. So that's the work that I would expect you to show. So for the next 6 problems, I want you to practice pulling this negative out and marking it as I. Okay, so for the top 3, those are perfect squares. And then the bottom 3, those are not perfect squares. So the bottom 3, you need to simplify the radical. You can't evaluate it. There's no square root of 8. Okay, simplify the radical using a factor tree, remember? So try those 6, and I'll put my answers up there in a minute. We already did root negative 4. That was 2i. Okay. If you do plus or minus on these problems that don't have an equal sign, I'm not as concerned about it. The big thing is when it's in an equation and you take the square root of something that you really need to have that plus minus. Okay? So give the rest of those a shot and then we'll talk. So for those top 3, check your answers there. So the square root of 25 is 5, and then the negative comes out as I, so you lose the root altogether because it was a perfect square. Okay, and then here, let's walk through number, that bottom left, that 8. So factor tree for 8. 4 times 2 gives you the 8. 4 can break down into 2 and 2, and you have a pair right there. And so some things come out of the radical, some stay in. The pair comes out. You have a 2 that represents the pair of 2's. And then anything that doesn't have a pair stays in. So the other 2 that's alone stays in. And so this ends up being, this is I root 8. And I'll put plus minus so that you can kind of see how it all fits together. 2i root 2. So the 8 becomes the 2 root 2, and then I typically write variables, right? If this was x, it would come after the 2, so I'll write it right there. That's the convention to write it that way. For 12, factor tree for 12, so 3 and 4, 2 and 2. So again, if it has a pair, it comes out, and if it doesn't, so there's a pair of 2 there, the 3 is alone, so it stays in the radical. So this is I square root of 3, and the 2 came out. The I handled the negative, and then the 2 root 3. And then number 24. 4 times 6 is 24. And then, actually, I'm going to do it the other way so you can see what happens. So 12 and 2, 2 and 6, 2 and 3, right? So the pair of numbers doesn't have to be on the same branch. I can partner up those two. Okay, so there's a pair. And then the 3 and the 2 are all by themselves. So this ends up being I, root, okay, 2 on the outside for the pair, and then 3 times 2 on the inside, which leaves me with 6 on the inside. Yeah.
Why did you put plus minus on the first one and not on this?
Because there's no equation.
What?
There's no equation. Like it's not as vital for you to put plus minus in there if there's no equation to begin with, right? This isn't like something equals something else. Okay. If you put it there, I wouldn't count it wrong. If you left it out, I also wouldn't count it wrong.
Okay.
But if it's in an equation, you absolutely must have it.
Okay. And
so I just put it there so you could see where it would go. But on these, since these are not equations, I'm not as worried about it. Okay. So that's I. Let's keep going. So the fundamental theory that came out that controls all of this is that the square root of -1 is equal to I. I equals the square root of -1. Okay? And that kind of begs the question, what about I squared? Well, so let's think about this. If I do 3, the square root of 3, and then I square that, what is that? Yeah, that's 3. The squared and the square root cancel each other out, and I'm just left with 3. So reason stands that if I were to do the square root of -1, which is I, squared, well then the squared and the square root cancel each other out. And so I squared is actually just -1. If you square a square root, it cancels it out, and you're left with whatever's on the inside. So if I square that square root, I'm left with whatever was on the inside. And that's going to help us on some of these later on this page. So let's look at the first two. And just so you know, I'm writing these along the side because these are two things that you should memorize. You really should memorize all the way up to I to the 4th power, but the 3rd and 4th power are really they're just extensions of this. Okay. All right. So we have these two complex numbers, and they call these complex numbers. This is the real part. The 7 is the real part, and then the -2i, that's the non-real or imaginary part. Okay? And so together the whole thing is a complex number. Those are complex numbers. Complex. A plus B I. Some number plus another number times I. So here we're adding two complex numbers. We have 7 minus 2i plus -3 plus I. And anytime we see parentheses, you should think, are they asking me to distribute anything into the parentheses? That's typically why they have them in parentheses, because they want you to distribute something in. Is there anything to distribute in here? Is there anything in front of the parentheses? No, no. If there is, it's an understood 1. And of course, 1 times anything is itself. So you don't even have to do that. If there's nothing to distribute, you can leave the parentheses right away.
That's just on this type of equation, right?
And then at this point, we can just combine like terms. So 7 and -3, well, that's 4. And then negative 2i plus I is negative I. We treat that like a variable. Like if it was x. 2x plus 3x is 5x. 2i plus 3i is 5i. Okay? It's not a variable. That's important for you to know. Because if I put x in an expression, that represents a number I don't know. That's how we use letters in math. We use them to represent numbers we don't know. I, however, is something I do know. I know what I is. What is I? Square root of negative 1. We know exactly what I is. There's no question about it. It always means that. Every mathematician on the planet knows that. Okay? It's defined, it's set, it's not an unknown like x. But we can treat it in algebra like we treat x. Okay? On part B, we have a negative. We have a minus here, so let's distribute the negative 1. So 1 plus 5i minus 3 plus 2i. Okay, negative times negative there. So this ends up being what? What's 1 minus 3? Negative 2. 5 plus 7. Oh, never mind. 5 plus 2 is 7. Okay. Yeah, we'll do one more. Distribute on this last one here. 8 plus 6i minus 8 minus 6i plus 6i. Negative times negative, thanks. So the 8 and the negative 8 cancel out. And you're just left with 12i. Still a complex number. Even though it's just one piece, it's still a complex number. Okay. We can multiply I. We can multiply complex numbers. So what is 7x times 3x? 21x squared. Because x times x is x squared. So 7i times 3i is 21i squared. But wait. Yeah, what is I squared? I squared is negative 1. I squared is negative 1. And so we can substitute I squared for negative 1. We can put negative 1 into it. I squared is equal to negative 1. So we can substitute it. So this equals negative 21. Because negative 1 times 21 is negative 21. Okay? So just because you're multiplying two complex numbers doesn't mean that it's going to produce another complex number. This one produced a real number, negative 21. And that kind of alludes to the idea that these are not worthless. Not that you care. So part B, why don't you go ahead and multiply these. What method do we have to use to multiply these complex numbers? FOIL, or double distribution. FOIL. Right? So 8. 2 times 5i is 10i. Negative 3 times 4 is negative 12i. And negative 3 times 5 is negative 15i squared. So you've got some like terms to combine, and you have an I squared. You can substitute. You should always substitute to get rid of the I squared. It's negative 1. I squared is negative 1. What's I squared? Negative 1. Do you think that's important to remember? Yeah, just a bit. So 8, 10, and negative 12, that's negative 2i. 15, I squared is negative 1. So 8 minus 2i plus 15. Where did I get the plus 15? Negative times negative. Negative 15 times negative 1. It's positive 15. And then 8 plus 15, what is that? Twenty-three. 23 minus 2i. Okay. The last one, part C, I want to do this one. What's the only difference between these two complex numbers? Yeah, that sign in the middle. We have a name for this. When you have a complex number, a plus bi, and another complex number that's exactly the same numbers except minus instead of plus, or the opposite sign there in the middle. We call these conjugates. Conjugates. Okay. So you should just remember that. I'm not trying to give you a hint or anything, but you're all better at math now, just a tiny little bit for knowing that. And that's a term that is going to get thrown around in pre-cal or college algebra or wherever you're going next. So I just want you to know that for now. So part C, these are conjugates. And we're going to see what happens when we multiply conjugates. It's something unique. So go ahead and FOIL these two together and see what you get. Okay, so if we're foiling these, negative 4 times negative 4 is 16. Negative 4 times negative 5i is 20i. 5i times negative 4 is negative 20i. And negative 5 times 5 is negative 25. I times I is I squared. And we have like terms that we can combine. We have this 20i and this negative 20i. What's going to happen to those? Yeah, those actually cancel each other out. Combine those like terms there. And then we also have I squared. What do we substitute in for I squared? Negative 1. Okay. Anytime you have an I squared, you can substitute negative 1 in there for that. So this is 16 minus 25 times negative 1. Negative times negative is positive. So it's plus 25. So this whole thing ends up being 41. And again, you have another example of where a complex number times a complex number leaves you with a real number, or a whole number. Okay? So, and that's going to happen when you have conjugates, when you're multiplying conjugates. That's one of the things, that's one of the reasons I'm showing you this, because there are going to be times later on in math where you have to find the conjugate and multiply by it. And so I want you to see why that's strategic, because it gets rid of these pesky i's. It would also get rid of a radical if you had to get rid of roots or radicals. So we've got to use this now. The whole reason we're using this is because sometimes when you're doing the quadratic formula, you end up taking the square root of a negative, and now you have a way of dealing with that. Okay? So we're going to skip those, and we're going to do two more problems. First, we'll do complete the square. So let's do complete the square with this one. Actually, no. Let's do this one. So first of all, this is not solvable by factoring, so we're going to have to use complete the square or quadratic formula. For time's sake, I'm just going to have you solve. Okay. So let's practice using quadratic formula. X equals negative b plus or minus the square root b squared minus 4ac over 2a. Again, you need to memorize that. And in this one, a is equal to 1, b is equal to 10, and c is equal to 36. So we have negative 10 plus or minus the square root of 10 squared minus 4 times 1 times 36 over 2 times 1. Remember from yesterday's lesson, this is the determinant. This is the determinant. What do you remember about the determinant? Anybody?
Positive and like a real.
Yeah.
And something like that.
Yeah. If it's positive, that means something. If it ends up being negative, that means something. Okay. You got to know that. You got to know that. If it's positive, it ends up being what? 2 real solutions. If it's negative, it ends up being 2 imaginary or non-real solutions. Okay, so what is 10 squared minus 4 times 36? What do you get in your calculator? Should I stop? Negative 44. Negative 44. Which means you have 2 real or non-real. What do you think? Non-real. You're going to have imaginary solutions here. Okay. So put that whole thing in your calculator and let your calculator do that. Don't try to do that in your head. It's a terrible idea on a calculator test. Let your calculator do that work. I don't care if you feel like you're really good at mental math. Why would you waste the points making a careless error when you could just use your calculator? Right? So you can do it in your head, but check it in the calculator. Negative 10 plus or minus the square root of negative 44 over 2. Factor tree of 44, 4 and 11, 2 and 2. You have a pair. So this is negative 10 plus or minus I, the negative, 2 root 11. And of course we write that as 2i. 2i over 2. Okay? Everybody wants to do this. You ready? Everybody wants to do this. They want to reduce the 10 and the 2. And they see that and they're like, awesome. 10 divided by 2, that's 5 over 1. And I can reduce that. That's great. But you can only do that if something came out of the root and can go along with it. Okay? You can only do that if both this value and this value, the 10 and the 2, both can reduce by the same amount. Okay? All 3 of those are divisible by 2. So they can all reduce together. Negative 5 plus or minus 1i root 11 over 1. Over 1. Which we don't even need to write that. Question? Okay. So that's where I comes into play in what we're doing. Using quadratic formula, you now have a way to deal with the negative. Okay. So last problem, why don't you do number 6 on your own? Do number 6 on your own. And you can do complete the square or quadratic formula. It's up to you, your choice. And then we'll compare answers here in a moment. All right, check your answer there. So if you did quadratic formula, it's on the left. Complete the square is on the right. You see, you get 2 of this. You get the same exact answer either way. I'm not going to tell you what method to use on the test. Some people want to use quadratic formula for literally everything, and that's fine. I can tell you, okay, so quadratic formula is probably not that much work than complete the square is on this one. For some people, I think it is, but I don't know. But man, there's going to be problems on the test where it's like it's 2 steps and you're done. If you solve by factoring, versus quadratic formula, which is like 7 steps. Okay, so the point here is that you can be strategic and to know what problems to use which method on, to think about it strategically. We're done with the notes. You can work on your homework. The homework is 5.9. 5.9.